Welcome to Hot Chips 25. Session 7, Mobility.
I'd like to introduce the first talk, which is the Hexagon talk from Qualcomm, the Qualcomm Hexagon DSP. The presenter is going to be Lucian Codrescu. I was just informed, actually, that last name is as familiar as I thought, that he's actually the son of Andrei Codrescu. So we're expecting something very poetic and funny from him as he gives this talk. And anyone who doesn't know who Andrei Codrescu is really needs to go find out about it. So he's the lead architect for Qualcomm's Hexagon family of DSP processors and the manager of the Hexagon architecture and microarchitecture team. He and his team have delivered 5 compatible generations of Hexagon. Before joining Qualcomm, Lucian had 7 years of industry experience with Freescale, Motorola, and General Electric. He has 78 patents granted or pending. Lucian received his BS and MS from Virginia Tech and his PhD from Georgia Tech. Let's welcome Lucian.
You had to go mention my dad. I could never follow him, so no pressure there. Yeah, so today I'm here to talk to you about the Hexagon DSP. A lot of people don't know about it. I've actually gotten questions over the past couple of days. Hey, I didn't know you guys do DSP. We do. We've been doing it for a while. Actually, if you have a smartphone in your pocket, that's one of the newer 4G LTE versions, you actually have multiple Hexagon cores in your pocket running right now. We've not ever talked much about Hexagon before because it's a deeply embedded core that for a long time was just programmed exclusively by Qualcomm, and there's really no reason to open it up externally. That's changing, however. We are slowly opening it up to more and more external programmers, and because of that, we're kind of unveiling the architecture, if you will. This talk is actually going to be the first public disclosure of kind of some of the details about what goes on inside of Hexagon. So with that, I'll get started. So the Hexagon processor is in lots of Qualcomm products. Here I show one in particular, which is the latest and greatest Snapdragon 800. This is a block diagram of the chip. There's actually 2 instances of the Hexagon in this chip. One is the modem processor. So we have a Hexagon core that handles basically all of the modem functions. It drives the modem, does all the modem processing. We have another one that's the what we call the ADSP, or the applications DSP. It's in the multimedia subsystem, and it handles all of the real-time media and sensors processing. This is the one that we're opening up, and this is the one that I'm going to talk to you guys about today. So what does this multimedia core do? What are the applications that run on it? It's actually evolved with the evolution of the core itself. So when we started the program, we were very focused on voice and audio processing. So speech coders and MP3 and post-processing, echo cancellation, all of that kind of stuff was run on the DSP. As the architecture and the cores have evolved, we've been expanding the set of applications that run. In the newer generations, we're now doing camera applications, still, video. We're doing augmented reality, computer vision. We're getting into gesture-based interfaces. We're doing video, and we're also doing sensor-based processing. So you can see that it's really sort of expanding the scope of the multimedia applications that are accelerated on the Hexagon. So as I said, these, we've had kind of an evolution here. We actually started the program in 2006. Qualcomm opened an office in Austin, Texas. We have a robust team there that designs the Hexagon DSP. About 2 years after that, we came out with our first product, which was the original Snapdragon chip. That was the first Hexagon. And kind of since then, we've been making generational improvements. We're now in our 5th generation. So Hexagon V5 is in silicon today. It's shipping. And the design team is very busy working on the next one. Through each generation, we've made many improvements in efficiency, power, performance. And we've also done a lot of customization and tailoring for the two main uses, which are multimedia and modem. So we have typically in a given chip, we'll have multiple versions of the Hexagon, one tailored for modem, one tailored for multimedia. So what are these modem and multimedia applications that we work on? First, I want to tell you a little bit about the requirements to kind of set the stage. So the first thing is everything we do is real time. So we're interested in doing so many frames per second or samples per second, whatever it might be. But then once we've achieved that performance bar, which is kind of required to meet the product, then it's really an exercise in optimizing for low power and low area. And that's where we spend most of our time. We have extremely aggressive area and power targets. And the way this works is, we have this performance bar. If we, for example, come out with a processor that's 30% more performance than what's needed, that's actually usually viewed as a very bad thing. We would rather take that excess performance and turn it into low power. So that's the environment that we work in. A few characteristics of the applications that I think are most relevant from the processor point of view. The things that we work on, we're a DSP and we do signal processing. There's lots of signal processing in modem and multimedia. But in addition to that, there's also a lot of control code. In the modem, the Hexagon core is really the only processor, so there's no separate ARM. It does all of the protocol stacks and all of the higher level control software that's needed in the modem. In the multimedia land, while the codecs themselves are usually signal processing type things, they're generally wrapped with kind of very rich frameworks, RTOSes, device drivers, power drivers, all this kind of stuff. And that actually usually does amount to a fairly significant amount of control code. The other thing that's kind of a characteristic of these applications is we deal with a lot of L2 misses. So for different reasons, in multimedia, the applications move a lot of data, particularly in imaging and video, and so we have to deal with that. There's a lot of L2 activity. In modem, the code footprint is very, very large, and so we have to deal with kind of all the L2 misses in code. So we'll talk about that. So what is Hexagon? What do we do to kind of meet these requirements and meet these applications? So I want to really highlight 3 things that we sort of blend together to really form what I think of as Hexagon. The first is a VLIW processor. So we need a multi-issue machine in order to meet the performance needs. And we certainly could never even think to do anything like an out-of-order processor because the power and area would just be completely unacceptable. So VLIW is a nice architecture. It's low complexity, it's small, it's low power. So that's the first thing. That's sort of the foundation of it. But the next thing we do is we've engineered a lot of innovations into the instruction set design. And I'm going to give some examples about this in a minute. But essentially what we're trying to do is to maximize the work per cycle. Our design kind of philosophy is that we're really trying to go for very high work per cycle at a low clock rate, and that's the way to get the most energy efficient computing. We also want to keep all the pipelines full because that leads to area-efficient computing, more MIPS per square millimeter. And then, of course, targeting both signal and control processing. Finally, the next thing that we bring is multi-threading, and this is a little bit unique for an embedded DSP. We do it for a few reasons. First, I mentioned the L2 cache issues that we have. We can't simply throw a big L2 cache at the problem. It's too expensive. So rather than doing that, we use multi-threading to mitigate the latency. But there's something else that we do with multi-threading that's actually very interesting and unique to our design. And that's that there's a really neat synergy between multi-threading and VLIW in that what multi-threading does is it hides pipeline latency. And so what we do is we tell the compiler that there is no latency, all the instructions complete in one cycle. And when the compiler is kind of freed from the burden of having to schedule for pipeline latency, all of a sudden you have a lot more instruction level parallelism to fill the VLIW packet. And so what happens is the compiler then is much better at creating packets that are full, and then we use multi-threading to kind of hide the pipeline latency. And so those two technologies kind of work very well together. So the next thing I'm going to do is kind of go through each of those points, each of those things that we blend together, give you a little more details and kind of a little more flavor behind them. So the first thing is the VLIW. We have a core that is a 4-wide machine, so we can have what we call instruction packets, bundles of instructions that are variable size from 1 to 4 instructions. We have a unified register file, so 32 by 32-bit registers, one set of general registers that's used for everything, so we don't have split address and data and all that sort of jazz. Unified register file is great for the compiler, and so that's what we have. It's also per thread because we're a multi-threaded machine. We have dual 64-bit execution units, what we call the XUs. Each of them handles all sort of the math type stuff. We do SIMD operations within 64-bit. So we have 8 16-bit max per cycle. We also do single precision FMAs, floating point. And finally, we have 2 load store pipes, both 64-bit. We can do 2 loads, 2 stores, load and a store. They also handle simple ALUs as well. So this is really kind of the VLIW foundation, if you will. So the next thing I want to do is I want to take you through some examples of kind of the instruction set innovations that we've done that make Hexagon kind of what it is. And I'm going to give 2 examples, one from signal processing, one from control code. So in the signal processing, what I've done here is just given an example to kind of illustrate some of the things that we do. So this is actually an instruction packet that was taken from the inner loop of an FFT kernel. It's doing one butterfly operation in the packet. So it's got 4 instructions. One of them is a complex multiply. So we're dealing here with complex math, fixed point complex arithmetic. So we have instructions that are kind of dedicated to complex arithmetic. Complex multiply does everything you need to manipulate the real and the imaginary, do all the multiplication, shifting, adding, saturation, packing, everything you need to do that operation. That's one instruction. We have a SIMD vector add and dual load stores, so 64-bit load stores, each with post-update addressing mode. And we also have a hardware-counted loop machine. So there's some bits in the instruction packet that say, hey, this is the end of the hardware loop. And we have some special hardware in the fetch engine that knows what to do with that, and it decrements the loop count, does the compare and jump to the top. So if you kind of look at all the stuff we're doing here, we kind of counted up the sort of intrinsic, the basic operations, the primitives, if you will, and it comes out to about 29 simple operations. Not saying that other architectures don't also have vector adds and stuff, they do, but this is just trying to give you a sense of sort of all the work that's done, kind of in one packet for signal processing type applications. So control code. I mentioned before that control code is also very important for us. And we've done a number of things to kind of improve this. I want to walk through an example. So here's just a really simple piece of code. I got a function, it takes in a pointer and a value, checks if the pointer is null, and then sort of adds the value to it +2 and stores it back. So this is what it might look like in kind of a traditional VLIW architecture. We assume here conditional execution. That's pretty common. So you do the compare to check the pointer is null, and then you do a conditional load and a conditional return based on that compare. You then add the two and add the value, which are serial instructions, store the result, and return. And so it took me 7 instructions, and I did it in 5 packets. I got 1.4 instructions per packet, which is not that great. So a few tricks that we do. We've introduced something we call .new predication, which is the ability to bundle a compare and the instructions that consume the compare in the same packet. So in this case, I can then take these conditional load and conditional return and pull them up and bundle them together into one packet. We are very heavy. We do a lot of things with compound instructions. So rather than doing 2 wimpy 2-input serial instructions, very, very simple instructions, we prefer to kind of create a 3-input add, which is an instruction that's smaller in code, it's more efficient, it accesses the register file less. It's just a better way of doing this code sequence. And finally, we have another one that we call new value store, which is a similar sort of trick in saying that store instruction can take as its data operand anything that was produced in the same packet. So we can kind of shrink those dependencies. And so now you can see we've done the same 7 instructions, but now in 2 packets, and we've greatly increased the work per packet. So how does this look over some applications? So here I've shown a number of applications in the multimedia space, computer vision, video, imaging, control, audio, and just looking at the instructions per packet. And you can see that it's pretty good, right? So we're doing north of 3 instructions per packet pretty much across the board, sometimes north of 3.5 instructions per packet. So you might say, okay, well that's great, instructions per packet, but the machine really cares about instructions per cycle. So what does that look like? But before I can get there, I got to go tell you about the multi-threading. So Hexagon's a multi-threaded processor. To the programmer, we presented it as just a very conventional shared memory machine. So we went, very clearly with the, path of least astonishment. It just looks to the programmer like three cores, all of them in shared memory, and we share the entire cache hierarchy. So the I cache and the D cache and the L2 are all shared by all the threads. Now, this is not the way it's actually implemented, of course. The way it's implemented is very different, so I'll talk about that. It's actually changed through the generations. I'm going to start by talking about the simpler, earlier version that we did, which was in Hexagon v1 through v4. We called, it's just an interleaved multi-threading. It's a basic barrel processor type organization. We have a 3-stage execution pipeline, and we basically just rotate the threads, right? So we have thread 0 dispatches its instructions. On the next clock tick, the next thread goes. And then on the next clock tick, the next thread goes, and they kind of just continue to take turns. The nice thing about this is that, on the next tick, T0, all of his instructions are complete, right? So by the time T0 comes around again, there's no latency. So there's no latency seen by the compiler, and that, again, allows the compiler to then do a better job at filling the packets. Now you might say, well, okay, that's cool. That's a simple scheme, and it's easy to implement and low power. But what happens if there's only one thread running? You just waste the performance, right? Well, so in the next version, in Hexagon v5, we've done a little bit to kind of alleviate this a little bit. And I should say that first of all, the applications that we run for the most part, are multi-threaded. So our objective in life is not to be the best single-threaded processor. You know, we really care most about efficiency. It's all about power efficiency for our workloads, and our workloads are multi-threaded, so that's actually the use case that we optimize to. However, you know, there are cases where threads are idle, or you can't load balance perfectly, or you get L2 cache misses, and then you know, we'd like to do something about that. So we just added some sort of simple hardware which, you know, skips the threads that are idle. So we just, you know, if one of the threads is not being used, we take them out of the rotation, we rotate the other ones, and we get some performance benefit whenever there's a packet that actually can complete faster than 3 cycles. And many of them do, because they contain only very simple instructions. So here I show some data to kind of show how this works. Got a couple simple benchmarks, CoreMark and Drystone. And what we did is we ran it single-threaded mode, and we ran the same thing, but just 3 copies of it. So you know, when the machine is fully loaded and there's 3 copies running, that's what we call IMT mode, and you get, you know, 7-something core marks per megahertz, or, you know, 4.7 DMIPS per megahertz. And then in single thread, you know, this is where DMT actually matters, and you can see kind of a little bit of extra boost that you get, you know, with this mode. Okay, so how does that look? So this is now the same applications that I showed before, but this time sorted differently, sorted into the multi-threaded apps and the single-threaded apps. And you can see, you know, that the actual now instructions per cycle is very healthy. I mean, for the multi-threaded apps, and again, this is kind of the place that we actually really focus on. You know, we're doing 3 instructions per cycle, which is very healthy. And even for the single-threaded apps, you know, the numbers are quite respectable. I mean, 1 to 1.5 IPC is pretty good. So just a little more competitive data. This one is just showing the Hexagon versus a quote-unquote mobile competitor. This chart actually comes from BDTI. If you want to go see who the mobile competitor is, and I'll get more data on that, you can look at their website. But basically just trying to show, you know, the work per cycle that we do is very, very good, actually. Okay, so power. So, you know, we've done all this work to create a new architecture and come up with all these instruction set innovations and develop tools and, you know, train people to use it. It's a huge investment. Why do we do it? We do it for power, because it's so important in mobile. And so I want to show you a little bit about the results, what you actually get. So this is really one of the quintessential power benchmarks for mobile, which is just MP3 playback. So, you know, you got your phone, you want to listen to music, you know, you want to have 1 million songs and listen forever. You know, this is the benchmark. How many hours of playback can you get? And here we show in orange, which is a phone based on Qualcomm product, and a bunch of competitor phones based on other people's silicon. The lawyers wouldn't let us say exactly which phones, unfortunately. So you'll just have to trust us that these are all kind of in the same class, contemporary, all competitor phones. And the power that we achieve is really quite good for MP3 playback. This is power at the battery. So this includes everything in the system, the CPU, the DSP, the memory, everything. So that's kind of a bottom line number. Give one more example, this time from the domain of computer vision. So in this case, we've got a function, which is a feature detection algorithm, and we've implemented it 2 ways. We've implemented on the ARM core with Neon, and we've implemented on the DSP. We can either call it remotely or have a remote procedure call and call it on the Hexagon. So what happens when we do this, when we offload it? Well, the utilization on the CPU goes down. Obviously, the CPU is no longer doing that work, so it goes down. That's good. Frees up more room for other things. The actual time to do the feature detection didn't really change much. It's actually slightly faster on the DSP. So the user experience, the responsiveness of the application is just as good. But very significantly, the power went down by 32%. And again, this is power at the battery, including the entire system. So that's a very significant number. One of the questions we get often is, we have this multi-threaded machine. Okay, how does the power scale with the number of threads, right? If I've got 3 threads, if I'm only running 1, do I have to pay the power of 3? And the answer is no. We've done a very good job of clock gating and custom clock design to kind of control the power so that it goes like the work that you're doing. And this is just illustrating, so the blue line is kind of the ideal case. 100% of the power when 3 threads are running, or 1/3 of the power when 1 thread is running would be the ideal. And then this red line is kind of what the machine actually can do. Okay, so I've told you a little bit about the hardware, a little bit about the architecture, power benefits. That's all great, but it's really not very useful without software. About 3 years ago, Qualcomm opened up the Hexagon DSP to our OEMs. So we started a program where we allow our OEMs to customize or put whatever they want on the Hexagon. That program has been going quite well. Pretty much all of the OEMs have active programs now with teams of engineers developing code to run on the DSP. And then about, I guess, a year and a half, 2 years ago, we went ahead and expanded the program a little bit to include ISVs, software vendors. And so we now have a small ecosystem of about 20 companies or so that are all developing code for the Hexagon in this program. And then what they do is they port their algorithms and their applications, they optimize for the Hexagon, then they turn around and sell it to the OEMs. And this program continues to expand. But we want to go more, right? And so what we've decided to do, and I'm actually announcing today, is open this up much more broadly. So we're going to release what we call the Hexagon SDK, which is everything you need to go program the Hexagon. And this is going to be opened up with, you go to the website with a very simple click-through license agreement. You can get the compilers and the tools and the documentation and the examples and pretty much everything you need to go program the Hexagon. I should mention that this link is not live yet. There's a Qualcomm Uplink conference next week, and that's where this is going to be kind of officially rolled out and turned on and go live. So, and that's my talk. I thank you. And take any questions.
We have time for just a few questions.
David Cantor. First of all, thanks for the great talk. Wonderful to see some details on this. Is the L2 cache that you're referring to there, is that also used by the microprocessor? And if not, is there any relationship between your L2 cache and the Crate core?
So it's a private L2 cache for the DSP. And it's unrelated to the Crate. The Crate has its own L2. And communication between the two is through shared memory, through DRAM for the most part. So in today's architecture and the current chips, the communication is kind of, managed in a conventional way, primitives and interrupts and cache ops and that kind of stuff. As we go into the future, we're looking at more better ways to do that, let's say. So,
thanks.
Jim McGregor from Tirius Research. Okay, now we look at Snapdragon. We're looking at this. You now have programmable CPUs, programmable DSPs, and programmable GPUs. So how do you kind of determine the optimal place to be running different functions when you're looking at offloading?
So great question. And the answer really depends ultimately on what it is that you're doing. And you kind of can't answer that question without intimately knowing the application. And the hope is that people know their in the current way, people have to know their applications and basically decide what's going to go in the GPU, what's going to go in the CPU, what's going to go in the DSP. So there's no magic there today. It's all kind of manually partitioned. And it's really up to the developer to do that. Again, as we go forward and Qualcomm gets better at heterogeneous compute, you may see more intelligent ways of doing that, but yeah.
Thank you.
Okay.
This is Sriram. Is the modem implemented completely soft on the Hexagon DSP?
So is the modem implemented soft? So the answer is no. The modem is a mix of custom hardware blocks and processing done on the DSP. The DSP serves the roles of running all of the higher level application code, as well as controlling the hardware, doing all the kind of real-time control, and in some cases doing data path operations on the modem as well. So
is it a different flavor of the DSP for modem versus multimedia?
typically, yes. We customize it in a few ways. We'll change cache sizes, then we'll have different frequency targets, and in some cases we have actually had features that exist in modem but not in multimedia. Yeah.
Thank you.
Right.
Okay.
Thanks, Lucian, for a great presentation. So next up is a presentation from Intel. It's Power Management Challenges in Wireless WAN SoCs. It's being presented by Gunnar Bublitz. He's currently a systems engineer with Intel Mobile Communications Group in Nuremberg, Germany. He's a power management architect of Intel's cellular modem product line. His responsibilities include the definition of power delivery, as well as the reduction of power consumption. Gunnar received a diploma degree from the University of Applied Sciences in Berlin in 2000. Gunnar?
Okay. Thank you, Don. So what do we have prepared today is a presentation about our challenges, and I'm coming directly to the agenda. So first of all, I plan to present the Intel solution of an LTE modem platform. I would. Better now? I hope so. Yeah. Okay. So I start again. So I'm presenting today the LTE solution from Intel. What kind of modem system we have. I wrap up with some kind of power management basics. What are the challenges? Also, what kind of solution we found for this? And I would like then to conclude and look forward to your question. So going direct to our LTE solution and where do you use it? I mean, typical cellular modems are used today in ultrabooks, tablets, smartphones, and all things. And what do they contain? You have a Wi-Fi, Bluetooth connection. Camera is quite obvious today, audio as well. Some could be even more, have Atom SoC already inside. We talked about this yesterday. Display is quite important differentiator. Power delivery is also some area which is differentiating between competition. Huge amount of memory is typical in case, and then we have some kind of RF section with power amplifier, RF transceiver, location information from GNSS, so GPS and other positioning system is typical on board. And today we focus mainly on the modem. So the modem, in comparison to the RF, which is quite dependent on the radio frequency bands or what RF you are operating on, the modem is dependent on the standard you're running. So we started with the usage of, let's say, texting, then it was going voice, so the GSM is a quite popular example, going a bit to SMS texting and then data. And here, so we got now some storyline with 3G and lately as well LTE. So you hear maybe quite often LTE, but what's in it? So what do you have from it? And LTE means actually that the round trip time will be reduced, so you have an immediate response on your interaction, and you really get a high data rate. So Outlook is soon really 300 megabits, and the real difference is keeping mobility. So this is what LTE will about. So having a look on our LTE solution for this year, maybe to guide you shortly through. So we have, I mean, modem is also, you can understand it like where the black magic RF is transformed to a new data stream again. So you can really see it like we have a front-end switch component, contains filters or the switch as such. We have a multi-mode, multi-band power amplifier. And then finally, the data gets converted down to the baseband information and then fed to the cellular processor, here the Xcode 716. Beside that, you might recognize that also some kind of power management or power delivery components are there. So we have in the baseband chip and the RF some switched voltage regulator. So going a bit more to the communication processor, some of you have maybe already have looked at it in the market. So it contains not completely astonishing structure. It's a CPU with running the caches and all other stuff. And then we have dedicated hardware accelerators, DSPs, and other stuff concluded with some on-chip memory. There is, of course, an external memory interface on it. And sometimes we tend to forget, oh, that's great, a piece of hardware, but it's just a part of the platform. So the platform thing, the RF, we don't talk today, but the RF stuff and the baseband, but all together in the platform, it is just a complement with software. So I have to talk about the normal software drivers, but also the network signaling drivers. So the network signaling drivers are keeping the connection to the base station. You could imagine that there's all kind of antennas around. So it's just one part of the system. So having shown the solution or physical, maybe going one step back and maybe going through some basics. So the first one, these are the targets, of course, turn off all idle building blocks. I mean, you need to have a fine-grained power management system for it. You should run the active building blocks with lowest supply voltage. Also, something not very surprisingly, though they shall not be active without a good reason. Also something normal. And we've seen that using on-chip memory is a very good measure to really reduce power consumption. The same goes then, you should really supply everything from a DC-DC converter when possible. So all obvious, but actually really keeping all of these kind of things really intact in the complex system. This gives the magic of the system to really have the low power. So how can I understand it? It's also, this is an understanding. So on system level, we have the use cases between off, deep sleep, idle, working, and you can see this is just a system level representation. So beneath that, you have several devices, CPUs, which can run quite independent or running quite independent from the system use case. So you have to adapt, you have to make sure that this is running all of these 5 principles. And this, as I said, is quite amount of work. So where do we need this kind of toolbox? So what are the challenges? So one of the biggest challenges in a mobile system or a cellular mobile system is concurrent operating of multi-radio access technologies. You have to think about it like this, that you have up to 3 or maybe more systems communicating with your mobile device concurrently, having own timing. So this is quite flexible and constrained timing of your instructions, etc. It should be quite cost sensitive, so you should think about shared resources. So how do we enable this? And one of the main objectives for us is, of course, then low power consumption. So this can't be done after tape out and so on, so you really have to tackle these kind of items very early in the stage. So I yesterday wandered a bit around and thought about what is a good example, and the good example looks like this. So I found one person that you look on it, I got a new information from the first application, and another one got a push email back. and another one again sends it. So what do we see here? So we see even the mobile is in your pocket, or maybe you look at it at the moment, you're toggling between active and idle states. And this kind of toggling is happening very often. It's quite dependent on your applications. So in the break, you can maybe count your applications, and then you can imagine how often your phone is changing. So you can ask, where is now my low power state? Is it the active I have to optimize or the idle one? What is low power? Is it that or this? So it's quite a challenge. So to give you some kind of evidence, we made some studies. So what you can see is that really 40% of the data packets are really smaller than 50 byte. And this is not a typo, it's really byte. So it's just keep alive and sending shortly, hey, I'm here, I'm back. So you really transport very small data packets, and you have this overhead of communication. And then you say, okay, it's happening once a while, but actually looking how often does this happen. So you can make studies with some kind of normal stuff which we all have on our phones, like a weather forecast, how the stocks are going. And you can see that the phone is responding every 30 milliseconds or every 300 milliseconds. So you do not do anything, but just the applications keeping the system intact. And then you can wonder, okay, I have an instant messaging client. Also, they differentiate. So they are sending more often or less often messages. So these are constraints. So one is the network, and the other one is the applications. And we really have to tackle them. So what are our solutions tackling them? I would like to illustrate this on a first use case on this idle mode. What is idle mode? Idle means everything for us. But idle mode in a mobile phone means the normal mode of operating, you have it all here now. So it means until you're in the plane and you switch it off or go to flight mode, your phone is typically idle. So it's waiting for some kind of message from the network to wake up. So you constantly turn it on and listen, is there something I missed or not? And now I have to understand that you have maybe 3 RUTs or even more systems parameter, so different timing. So what do I have? I have to make a very efficient offloading of the CPU, because always switching on CPU takes some time, computing, shutting down. So this is a screenshot of a battery current over time. And you can see that it's quite hard to see, but in the off period, or where you don't think it's really low, so it's really not power gated or in standby operating or whatever. And then you power it up, and dependent what you're doing, you can do frequency and voltage scaling helps as well. Okay, idle mode, quite uninteresting because we wanted to talk or have data call sooner or later. So data call means for us now, okay, I'm sending an email, I receive a big huge of new presentation. But for the modem, it means you have to be hardware prepared for the maximum allowed use case, for the maximum download speed, etc. So you have to have, for example, this is an example of an LTE Cat 3 with a 20 megahertz bandwidth. You should be able to receive 100 megabit and send to the network back about 50 megabit. Okay, great. But now you come around, you take this phone with you, you're coming around to the US, and you see, okay, my network operator have only a 10 megahertz channel for me. So the system have to automatically adapt. And I mean, it don't have to, but we see it quite positive that you reduce the power if you're not using the full capabilities of the system. So here you reduce, due to clock scaling, the amount of power you're consuming. Another measure is actually not always we're transmitting with full output power, especially in urban environments, antennas, or the link is quite good. So you have to transmit with full power, and there are some scenarios where you can really optimize your receive chain and have a benefit here as well. And then you can also argue, yeah, I'm sending just very shortly, so do I really have to have the full data speed, or I'm not sending uplink, so I just receive data? And also here we have implemented several measures with voltage and frequency scaling to really adapt to the actually needed performance and give the customer the most benefit when it comes to power consumption. What else do we have? This is a fixed, unique one, but you might say, okay, I have this functionality of 3G or LTE. I would like to scale it also with different segments. So I have here an example of a, let's say, called feature segment. So here the functionality is very important for sure, but I have to be area and cost optimized, so I run only with a single switched mode voltage regulator. On the other hand, I have sometimes systems which are really in the performance segment, and here I say, okay, performance also means performance with a low power consumption, so I use more regulator. So these are measures you can scale on chipset, on hardware level, but there are other things as well to consider. So actually the network operator have also quite a huge impact on the current consumption or power consumption on the system. So the phone is not really deciding on its own if I've been connected or if I am in standby mode. So this all comes down from the network. So in the network, you can stay in a connected environment. It means you are always connected. You can send immediately. You have a low latency when sending something, or you're in idle mode, and then you have a lower power consumption. But now we have seen that sometimes the applications move us out of it because it's requesting some data back and forth. So the application have an impact, but also the network operator can have an impact while setting or selecting the network parameters. You call DRX parameters is the time between this new reception, so when you wake up. So there are some measures to be optimized on this area as well. The message I wanted to give is the chipset alone is needing, it's very important for the chipset to adapt to the environment, to really optimize what is confronted with, but it really goes beyond the device boundaries if it is low power. Actually, I'm quite good ahead of time. So would already finish and conclude my presentation. I hope I have given you some good overview what the LTE solution of Intel at the moment is prepared or is doing to have an optimized power management scheme. I hope I have given you a small brief about the LTE modem power states and how they are bound to application scenarios and what are our barriers. Finally, it's also showing that we are using state-of-the-art fine granular power techniques. So I have now some time for questions, so I would be happy for questions about the presentation I showed, or of course questions which I have not covered. Thank you.
Do you guys use any envelope tracking, and do you have any interest in doing so if you don't already?
Envelope tracking is a measure to really reduce the active current of the overall system, and is a supported feature, yes.
All right, thanks.
Hi, I'm Sotiris Bantis from Helic. Can you comment on the need to use discrete components for your voltage regulators that go into the high performance segment? Is there a need for discrete components, or have you been successful in integrating the discretes on chip?
Thank you for that question. This platform so far shown is having external discrete component for, let's say, standard buck converters or buck boost converters, So at that point in time, we haven't integrated components as such.
Okay, thank you very much.
Thank you.
Hi, I'm David Hansquin from Qualcomm. The previous presenter talked about the DSP being responsible for controlling the modem in those devices. I was wondering if you could elaborate on the CPU that you showed in your diagram, anything about the architecture or instruction set for that.
Also thanks, and of course it's an obvious question having the talk before. No, I'm sorry I can't disclose details about this here. No. Thank you.
We have time for about 10 more questions.
Okay.
You know, that's sad when you have someone from Intel here ready to answer questions and no one's going to get up. Come on. Dang it. All right, let's give Gunnar a hand. Thank you.
Thank you.
Good work, man. All right, the next talk is 5th generation touchscreen controller for mobile phones and tablets by Milton Ribeiro. Milton is a vice president at Cypress Semiconductor and the chief technologist of its TrueTouch business unit. He has engineering and master's degrees in electronics and 22 years of professional experience in large companies like Philip Electronics, as well as startups. He holds 7 issued patents in the fields of data encoding, power management, and capacitive touch sensing. Let's welcome Milton.
Thank you for receiving me and accepting my paper. And I hope you enjoyed the little talk here. I'll be happy to talk a little more. I don't have that many slides. What I want to talk about today is, why do we have 5 generations of touch controllers, right? Doesn't sound like that complicated of a problem to solve, but it's actually not that easy thing to do to deliver low cost and to deliver low power, which are essential elements of this technology, right? So I started with the first slide with what were the design goals? Why did we decide to go do a 5th generation after the 4th generation, right? Simply because the landscape and the problems that you're trying to solve actually changed in the year and a half that took us to make 4th generation. So we had to evolve again, and by the way, they're going to change again, and we're going to probably have a 6th and a 7th generation here. So the design goals here were, we want to be able to make quick derivatives of the technology. And why do we want to do that? Because there is such a large class of different devices that use touch technology nowadays, and they need to be so cost optimized that you actually almost need to have one class of devices one class of ICs for each one of those devices, right? A smartphone is going to require a different controller from a tablet, which is going to require a different controller for a notebook, at least if you want to deliver that cost optimized and power consumption optimized. So when we talk about quick design of derivatives, what comes to mind and what we are doing is we have a platform-based design. So we have a basic platform that gets scaled for the different class of problems we are trying to solve. And I'm going to have a picture later on that's going to show a little bit about that. We have a scalable analog front end. So basically the channel that's used to scan the capacitive sensor is designed in a form to be scalable. So we can actually quickly make derivatives of that. We have a scalable DSP data path, which is designed specifically for the kind of problems you are trying to solve. And we have a flexible hardware platform that allows us to, by using algorithms implemented in firmware, quickly modify the controller to deliver different kinds of advanced features. The main goal of the platform is a superior noise performance. By the time we got 4th generation controllers out, noise suppression had already become a significant problem in making cell phones. When I say noise suppression, just translating to something that's much more understandable, when you take your mobile phone and you put on the charge and then try to type a message on the touchscreen, many of you may have had the awful experience of typing A and getting an S and typing R and getting a T or whatever it is. That's typically caused by a type of noise that's called in the industry charger noise. It's basically a type of noise that gets induced on the screen when you close the loop with your finger, right? There is a capacitive loop, and you close that loop, and that injects noise there that's generated by the charger. The cheaper the charger, the worse it is. Those nice $499, iPhone replacement chargers that you guys buy in Amazon are the worst possible ever, right? That had become a serious problem in the industry 2 years ago, and we designed the 5th generation architecture specifically to deal with that, to make that not be the case anymore. Actually, I think if I go back here, you can see that noise is the symbol here of the presentation, because that was the specific goal of that, architecture. I talked about finger-coupled noise, charger noise, right? There is this goal of getting better than 40 volts peak-to-peak rejection, which we have accomplished with the architecture. But also display noise, being able to directly laminate a sensor onto a noisy LCD was very important as well, because noisy LCDs are typically cheap, and many people are going to want cheap, and you want to make it thin, so you don't want to have any kind of shield or air gap to help suppress noise. So being able to deal with that was important as well. The third main design goal for this was innovation acceleration. What do I call innovation acceleration? Be able to have an architecture that's going to support advanced features. What do I call advanced features? Some of you guys may have played a little bit with the Galaxy S4 and the hover function. That's something that's an advanced feature. Being able to use very nice passive stylus with thin tips, that is an advanced feature. Active stylus that deliver a superior experience when trying to capture text, that's an advanced feature. When you scan, being able to touch and dial a number on your phone without having to remove the sleeve gloves, that's an advanced feature, right? And we had that in mind when we designed this. So we'll talk about design goals. Let's talk about the architectural elements of the solution. The solution basically has 3 levels of elements, let's call that, right? We have a CPU. You have a Cortex M0 running at 48 megahertz, very, very low power, very efficient. It's mainly there to do what we call finger tracking processing, basically, after you decide that there are fingers on the screen, where those fingers are and where they have gone, and that kind of thing. Kind of a 2D, very simple 2D image processing. And also the communications, right, with the host. Outside the CPU, you have a low-power microcontroller, infrastructure that does all the kind of on-power management kind of stuff. We have a analog front end, which is basically the channel. It's the analog stuff that allows you to scan that channel. We have high voltage signal generation. In order to deliver superior or high SNR, you want to scan the sensor with high voltage. So we have on-chip switching power supplies to actually, capacitive power supplies to generate 10 volts out of your battery, out of the typical 3-volt power supply. We have the configurable DSP data path. It's not programmable. It's configurable in the sense that there are a set of different filters and activities that's capable of doing, and you set them up, and that delivers very low power, cycle by cycle processing of the samples. And there is a little list here. I'll talk about FIR, window filters, median filtering, a few other kinds of nonlinear filters there. There is digital quadrature demodulation done in hardware for active stylus, right? Real-time noise metrics. So how do you decide what kind of a noise suppression strategy you should follow? You basically have to have an idea how much noise you have and the frequency of the noise. And basically, the configured data path allows us to figure that out. And there is very simple 2D image processing algorithms that allow hardware acceleration of some of these functions that is needed, especially for the bigger screens. We also have something that's pretty useful, and I'm going to give you a example later on how that helps. Is a table-driven sequencer. You basically have the ability to do a very flexible ability on how you scan the sensor and the different modes you can do that. That's very, very unique to the way Cypress does this. So this is a overview of, a channel-centric overview of the chip. We basically have the receive channels. We have the TX pump, which produces the high voltage signal that's used to scan the capacitive sensor. And then we have in blue there, here, basically what we call the channel engine, which is the configurable data path and the hardware acceleration blocks. And that talks to the, the CPU on this side here. This is one instantiation of the architecture, is what we call TSG5L, is our chip that is geared towards the phablets, right? The 5-inch plus phones up to 9-inch tablets. It's basically, as I said, a Cortex M0. Everything that is up here in gray is our computer architecture. The Cortex M0, 64 kilobytes of flash, 12 kilobytes of SRAM, 8 kilobytes of ROM. Depending on the instantiation we do, the size of these memories change. Those are the size of the memories for this particular instantiation. We have the infrastructure for power management and all. And this is the channel with its 58 TX and RX signal scanners, basically. We also have an infrastructure for communication with the host that supports SPI and I2C. Let's see. And that's the die. It's a picture. I mean, we are sampling these parts to our customers today. We have been doing that for a couple of months now. And it's going to be seen in many, many, many phones in first quarter of, let's say first quarter of next year. This is a abstraction of the channel itself. It's not actually very complicated. It's meant to be very low power and very simple. The complexity is actually on what comes after that to be able to separate noise from signal. But it's basically an integrator with a 30 picofarad capacitor. In front of it, we have an attenuator that can get engaged in the presence of very large noise to be able to avoid channel saturation at any cost we can. We have a IDAC that allows us to baseline the signal so that the ADC is only converting signal of interest instead of all that charge that comes in. And we have a very simple 8-bit SAR, which does the job, running at up to 500 kilohertz. So we can actually do 1 mega samples per second per channel. This is what I wanted to show. We talked about table-driven architecture. There is a lot of cool things that this chip can do without actually having to use any complexity here. Our ability to configure the channel to sample things in a very flexible way allows us to control carefully the integration time of the channel and the so-called reset time for how long the channel is actually not sampling. And by playing with those parameters, and if you play with the mathematics, allows the channel to become much narrower than it could have otherwise been. What I'm trying to show here is what we call D67 integration. What we do here is that the channel actually integrates the signal for 2/3 of the time, and it resets and gets blind to the signal for 1/3 of the time. What that allows to do is actually, by design, remove the third harmonic of the noise susceptibility of the channel, right? Normally, if you don't do anything about it, the channel is susceptible for the fundamental frequency, which is the scan frequency you're using to scan the channel, but also the third, the fifth, the seventh, the ninth, and so forth harmonics of the signal. By actually using this technique here, we can eliminate the third, the ninth, and so forth as the harmonics without ever actually have to do anything else. The other thing we can do here, that's actually shown here, it's actually not shown here, but by actually playing with the windowing, whether you use a rectangular or a Blackman window, we can make the channel reject more out of band with a wider main lobe or the other way around, and that depends on the type of noise you're trying to fight. On the bottom here, we talked about the chargers. That's the typical noise response of the Duracell charger, which is a very nasty one. If you guys want to avoid having troubles using touch on your phone, try to choose a different brand. That one is pretty bad. I hope there is nobody from Duracell here. You guys can see, I mean, this is 100 kilohertz here, 200, 300, 400. It has a pretty heavy load of content between 100 and 300 kilohertz. And a lot is still shown up in its harmonics. If you guys look at here, where these guys, the peaks here, and where this stuff is here, if you don't eliminate the third harmonic, there is a ton of noise that you're going to bring in. And the other thing that's very cool is that you guys read about, if you guys ever read about combating charger noise in touch controllers, you're going to hear frequency hopping, right? I mean, everybody talks about frequency hopping. Well, I mean, where do you hop, right? There is not a lot of place to hop here. Real chargers have very wide band noise, makes hopping a very, very tough thing to do. Sounds good on paper. In practice, you're going to actually have to deal with the fact that there is a ton of noise being thrown in your channel and how you're going to handle that. So here there is a comparison between our Gen 4 and our Gen 5. It's just to give you some numbers. If you look at this, there are some interesting things that make a difference, and we try to use that to make for better noise suppression. Here's one important one. Noise comes in these channels as charge. Those are AC coupled channels. And in Gen 4, we would saturate the channel at 8 picocoulombs per edge in the signal, right? And when we are talking about 40 volts peak to peak, you're talking probably 10 times more than that, at least, right? Depending on the thickness of the cover lens and other parameters. Well, I mean, in Gen 5, we can go as high as 200 picocoulombs per second per edge, depending on the setting of that generator. So the idea of this, keep the channel linear, don't let it saturate. Maximum scan frequency, that's very important. You guys saw the Duracell charger, how it has noise spread between 1 and 300 kilohertz. You want to move your channel outside that. Most of the chargers out there have heavy content up to 200 kilohertz. So if you go very high frequency, you are basically moving your channel out of the, the band of interest, basically, of the noise. What else is interesting here? We have a flexible sequencer that allows this D67 kind of scanning, which is very useful if you're trying to deal with charger noise. Some of the rest is the same, with the same 10 volts scanning. Very low power, both designs. It's small, cheap, low power. Those are the design goals, and we delivered on that. Current status and future developments. I mean, we have 2 instantiations of this architecture already out, what we call TS25M and TS25L. TS25M is geared towards phones smaller than 5 inches. As I said, L is between 5 and 9 inches phones of all kinds of phablets and tablets. We are working, and soon we're going to be announcing solutions for bigger screens, for bigger tablets, 10 inches and larger, and for laptops up to 15 inches. That's it. Thank you. I'm Milton. John, which is my colleague in marketing, unfortunately couldn't be here. As a marketing guy, he's visiting customers. That's good for him. Okay? Thank you.
Any questions?
I don't think the Synaptics and Atmel guys came.
Yeah, I think it's the afternoon lull. All right, I guess with that, we're going to call, oh, wait.
What do you think about, going in the connect direction, going to 3D, scan motions above the screen? Do you see that eventually?
I mean, there is a lot of that moving in the smartphone today, right? I mean, you have a camera there. You want to make use of that camera. I'm not sure that Kinetic gives you a lot, because the idea of Kinetic is actually having 2 spaces that you're looking at. You're looking at the infrared with the grid to look at depth, which, in front of a phone here, if you're doing gestures here, may not help that much. But just that camera, if you could afford, from a power consumption standpoint, to keep it on all the time, would be a great vehicle to do gestures. But that's exactly the problem, right? The camera is pretty high power, so it's difficult to. That's the issue. Now, yeah, if you can figure out when to turn on, that's a powerful way to give some more flexibility. There are other approaches as well. I mean, I don't know how familiar you are with the Galaxy S4. The Galaxy S4 has actually a set of infrared sensors on the very top. And Samsung has used them to implement very simple gestures, left to right and right to left, which is cool as well. Those are reasonably low power sensors. You use them typically for face detection when you're answering the call, so that you can turn off the screen and the touch. So I see that happening as well. To be honest with you, I don't think there is going to be a winner. Okay, that is going to be the sensing technology that's going to be all in for smartphones and everything else is out. I think there's going to be a continuous combination of different types of sensors to give users a much better user experience. And that not only touch or gestures, but you have movement sensors that allow you to decide that the user actually picked the phone and is going to answer, and the combination thereof makes for powerful UXs that we can't even envision yet.
What about differences between the phone and the tablet? Will they always be perfectly identical, or there will be different?
There are differences. I mean, on the tablet, taking notes, think about it, right? If you want to make a tablet with a nice stylus that actually is usable, right? You're going to want something that where you can put your hand there and you can write like you write on paper, right? Doing that with a passive stylus, as they are called, is not a very easy task to do. So you want an active stylus. You want something that's going to have buttons and pressure sensing, and is going to give you that additional experience. So I think active stylus for tablets is very key. When you think about a small phone, I mean, you're not going to put your hand there, and even the experience of taking notes on that is never going to be great. So a passive stylus is more likely to be acceptable. The noise environment, the charger armor in phones has been more critical than it has been in tablets because, you are not really using your tablet connected to the wall normally, right? Your phone, you may want, I'm going to make a quick call, and you want to make the call, right? So there are differences. They're not that huge. The main difference there is, and that is the big issue, is that the cost of capacitive touch, capacitive sensing, grows quadratically with the screen size. Yeah, it's a mesh, right? So the number of nodes in the mesh given a certain pitch grows quadratically. So the cost of the silicon and the cost of the sensor itself goes quadratically. In the case of the sensor, it may grow exponential because the yield loss grows exponentially with size. So if yield is a main issue, that becomes a big deal. So I think touch in the very big screens is ripe for a different approach completely that doesn't involve capacitive touch. Capacitive touch may not be the best approach for really large screens, right? And there are other technologies coming up now.
Thank you.
You're welcome.
Other questions? Also try to go to the microphones too for the stake of the cameras, etc. All right.
Thank you.
With that, we'll end the session a bit early.